Hi, my name is Pranav Sridhar, and in today's lab, I'll be calculating the mass of the black hole with the help of Newton's second law of motion and momentum principle. We start from the fundamental momentum principle and then divide both sides by delta t. Since dp dt is a good approximation for delta p over delta t for small delta t, we set them equal to each other. Now we split the momentum vector into its magnitude and its unit vector. Since both magnitude and the unit vector change in time, they are treated as two separate functions. With the help of the product rule, we take the derivative of dp dt. The first part that we get from the product rule gives us dp dt's parallel component, and the second corresponds to dp dt's perpendicular component. dp dt's parallel component and perpendicular component are equal to the force's parallel and perpendicular component respectively. The parallel component is useful in looking at changes in speed, while the perpendicular component deals with the change in direction or curviness. In our lab, we are exploring the elliptical motion of the star around the black hole. Therefore, both the perpendicular and parallel components will play a role. Also, as the lab instructions mentioned, we will assume that the only force acting on the star is the force due to gravity by the black hole. Hence, net force is equal to that. As we'll see later in the lab, we are able to calculate an average mass with the help of the code implemented on GlowScript. But before we discuss the lab in detail, let's talk about why we are interested in calculating the mass of a hypothetical black hole. The fact that just by analyzing the change in position over time, we are able to predict the mass of the black hole just goes to show how powerful Newton's laws of motion are. Also, this allows us to create computer models to make predictions in the future. Here's the motion of the star around the black hole. You can notice that the star has an elliptical orbit and that as it gets closer to the black hole, it moves faster and then begins to slow down. The reason behind this will be explained later. Now let's take a look at the code. As you can see, this is a snippet of my code which I used to set my initial conditions. The variable g represents the gravitational constant, and the mass of the star is given in the instructions. Delta t is set to 86,400 as that's the number of seconds in a day. Further down, I've created a variable m, which will be used to add the mass of the black hole at each iteration to help calculate the average mass later. In my calculation loop, I set fnet equal to dp dt. Later, I set dp dt's parallel component to d magnitude of p over dt times p hat, which is what we had derived earlier. Fnet parallel is then set equals to dp dt parallel. And since dp dt equals the sum of both its parallel and perpendicular components, we can simply set dp dt perpendicular equal to dp dt minus dp dt parallel, and fnet perpendicular is then set equal to dp dt perpendicular. Something important to keep in mind is that the parallel and perpendicular component of the force add up to make the force. However, the magnitude of the components don't necessarily need to add up to make the magnitude of Fnet, as seen on this slide. This is also confirmed by this graph. Another interesting thing in this graph is that the peak in Fnet corresponds to the time the star is close to the black hole. This makes sense as the magnitude of Fg is inversely proportional to the square of the distance between the black hole and the star, as seen in this formula. Since we're solving for the mass of the black hole, we first have to isolate the mass of the black hole from the equation. The steps are shown on the slide. Using the formula, we calculate the mass of the black hole at each iteration. Given that the force changes throughout the loop, the mass being dependent on force also changes slightly. Therefore, we sum up the masses calculated at each iteration and then divide it by the number of iterations after the while loop is ended to solve for the average mass of the black hole. The average mass we finally get is 1.44958 times 10 to the power of 34 kg. To answer the what does it mean question, there's an obvious answer that the net force can be measured while the rate of change in momentum can. However, another interesting thing is that in the beginning, when I derived the perpendicular and parallel components, I said that the delta p over delta t is equal to dp dt for small delta t. However, our delta t is a day. So the question is whether a day is a large delta t for a star orbiting a black hole or not. And there's no right answer to this, but it's definitely something to consider when looking at the accuracy of our answer. To answer the what if question, we need to take a look back at what the mass of the black hole equals to. As you can see, it's dependent on the net force and the distance between the star and the black hole. So if the orbit were to remain the same, it is safe to say that these values are the same for this black hole, and hence it has the same mass as the previous black hole. Thank you for listening.